So in the last video, we checked the runtime of the fancy median algorithm that we found, right? The one that would find the median value of an unordered data set. And all that work went in to show us that it actually has a worst case that's worse than if we just went and sorted the data and then picked the middle value. So that's kind of, discouraging. We put all that work in and we find that it leads us nowhere. But we remember that with the quicksort algorithm, if we put some sort of randomness into it to make sure that the pivot that we pick, that x1, is not bad, then it's going to be quick. It's going to speed up. So if we invest a little bit of time to make sure that the pivot is going to be good, then the algorithm will actually be worthwhile and we didn't just waste all of our time. So we are going to take a look at that right now. How should we set this up? So we're going to introduce the randomness, and essentially it means that we're going to want to make sure that let's get a diagram here to draw this. So let this be our data, right? Now, what would a good pivot be, right? The median is here, right? This is our data, and this would be our median. And we're assuming that this is if our data was sorted, right? So this is just theoretically our data sorted. The median is obviously the value that's right in the middle over there, right? And if you're talking about percentile, this would be the 50th percentile. Your median will lie along the 50th percentile. Now, what would be a good pivot, right? A good pivot is as close to the median as possible, right? So anything over here, this is a bad pivot. Anything along the edges here, like here as well, those are bad pivots. So we want to avoid those values because in the long run, even if just randomly picking is quicker than, trying to put a bit of strategy into our pick, which is the random, but we want to have some strategy with the random, it's going to slow us down way too much if we have one of those bad picks, right? So we want to have something that's going to be, let's go ahead and pick something over here. This will be the 25th percentile. And we'll put the 75th percentile. So anything in this region over here, it's 50% of our data, right? So we have to remember this is 50% of our data. It looks a little bit bigger because I think I didn't draw it to scale. But this is going to be 50% of our values. So if we assure that our pivot is going to be somewhere in that range, then it's going to split our data up with the recursive calls enough so that we're going to save time. Because the more we keep splitting it up, the more data we throw away that will not be included, right? The data that we know is going to be out of the picture entirely. So we're going to want to find something that's going to split the structure. So we want to pick our pivots to be in that 50% that's going to be green. Now let's say that we went ahead and we picked a pivot, right? Let's say our pivot was inside of here, and our pivot, let's go ahead and erase this. Get out of my way. I need some room to work here. Get out of here. Get out of here. Let's say we picked a pivot that was right over here. So this is the pivot that we pick. We know we're automatically going to create our sets, right? So we'll have our sets over here. This will be SL, the values that are lower, the left set, and we'll have SR, the right set, the values that are going to be greater. Well, we will know here that the pivot is going to be, the median, is going to be in the SR region, right? The bigger region is going to have it because that's how it is. We can cut off the SL region. We know it's not going to be inside. Now, based on where we picked these values, right? What inequalities can we write, or which, little just limits, I guess, if you will, that we can write to get a little bit of an idea here? Well, we know that the pivot here is clearly going to be for n. We'll see what I'm drawing here. Go ahead and write it out here. It'd be easier if I write it. So the size, we have the size of the left hand is going to be bigger than 1/4 of our data, because we know right here we can see that we are over the 25% percentile, right? So the pivot is greater than the 25th percentile. So we're can be able to write that. And we also know obviously that it's going to be less than or equal to 75% of the data. So we have that right there. And we can write something about the other one, the SR. We can go ahead and write the exact same thing. So we have it. There we go. So we can write that about both of our data sets, right? We know that the SR is going to be less than 75%, and we know that this one here is going to be greater than 25%. So, and essentially you can have the other parts of the limits as well. So a good pivot is going to be one that's going to be between 25% and 75%. So to go about solving all this, right, I think I'll include in this video because we haven't really covered much right now. It's going to be a long video. We will say that we're going to say anything that's not in there is going to be called bad otherwise. So we're going to let T with the thing on. I'll explain that in a moment. Now, because we are dealing with probabilities, right? We can't use running time when we're doing something that's deterministic, right? So we're going to have to use expectancy instead. We are going to pick a pivot. We're going to do n-1 comparisons. Regardless of what pivot we do, we have to compare every single value. So we will do those n-1 comparisons. And then how do we know if we have a good pivot or a bad pivot once we do those comparisons, right? We know we have a 50% chance of picking a good pivot. And obviously a 50% chance of getting a bad one. So with that range we have selected, we can go ahead and write out with the bar on top. We have that 50% chance. This is what the 1/2 here, the half is going to be. 50% chance, 3/4n, plus the 50% chance over here of n-1 plus big O of n, right? So let's go ahead and take a look at all this here. We will go ahead and we will label this with yellow. If we have a good pivot, and the worst case for the best case, so if the worst case for getting your good pivot is going to be that you're going to contain 75% of your data, right? That'll be the thing that we have here. You have to 3/4, and will be if you have the, the worst case of the good case. And this over here is, if you have, if you get a bad pivot, right? And once again, this is the worst case. So we're still writing those worst cases, right? The worst case for the good pivot is that you have 3/4 and data. If you have the worst case of the bad pivot, we already know that's going to be n-1, right? The bad pivot's worst case is that it's one of the values right on the end, and you have to go through every other value minus 1. That is going to take a lot of time. So we're starting to build this together, right? So it still doesn't seem to fit the master's theorem, right? We want to be able to, we know this is divide and conquer. We can't get back to the master's theorem just yet though. So how are we going to, I need to scroll down if I'm going to show you. Okay, this is starting to fight with me, so I'm going to start to get aggressive here. We know that the T with the little sign on top of it is going to be expectation time. So now we want to turn this into T of n, right? So we want to actually have something. So we're going to bump out that inequality over here. Go ahead and write it like this. Okay, so the way we have this written over here, sorry, we should still have this here, and we still have this. So we got rid of the -1 over here because the -1 is really not going to matter that much in the long term. But we see over here that we have two similar terms over here, right? These are similar terms, so we can actually go and we could bring this to the other side and subtract it. And then obviously you would have, we can have 1/2 expectation time here, less than or equal to 1/2 expectation time 3/0. This is just a lot of writing over here, but just bear with me just for one moment while I write this whole thing out. It's a lot of writing, but once it's all written out, it makes a bit more sense and it's a bit more clear. So now we have all this here, and we have, if we want to, bring this to the other side to just get it back to the same terms we had before, well, this is going to cancel out because we're multiplying both sides by 2. And obviously the 2 to the big O(n) here, it's not really going to matter. So we will still have 2 over 4. And there, now we only subproblem. So the reason why we couldn't use the expectation time was because we had those two subproblems, right? We had the one with the worst case, and we had the one with the good bad pivot and the one with the good pivot. Even though both were worst cases, we had the one with the good and the one with the bad. And that was obviously we couldn't do anything with it. Now we have the one thing, and we can use the master's theorem, right? Now it's in the form that we know. So we can actually go ahead and we can extract some data from here. So what do we see? What's the value of A? Well, we don't see anything, so that's going to be 1. What's the value of B, right? Well, the value of B over here, it's going to be a little bit strange, but it's going to be 4 over 3. And what's the value of D? Well, we don't see anything, so that's obviously going to be 1. So what case is this, right? Well, we go ahead and we compare the A. So A is 1, and we are comparing that to B to the power of D. So 4/3 to the power of 1, which is B to the D. What is the comparison? Well, this is going to be bigger, and this is going to be case number 1. And case number 1 said the running time. Remember, a lot of writing here. I want to make sure it's all clear. Case number 1 says that the running time is big O n to the power of D. What is D in this case? D is equal to 1, which means our running time is big O of n. But remember what we're saying, right? We're still in expectation time, so we have to make sure we write this properly. We are expecting linear time, which is big O of n. So picking at random makes this a lot quicker, like a lot quicker, right? This is, we went from polynomial time to linear time just by doing that. So I guess I'll do a quick run through of it again. I know this video went on for absolutely forever, but it's a confusing thing. But so we see here, we wrote out that we now create these two universes essentially, right? We have the universe where we pick a good pivot and the universe where we pick a bad pivot. Now we want to have the worst case scenarios for both of these because worst case scenario time is the most important time, right? We want to make sure that we can, if we can't write an actual thing straight up, we want to make sure that we're going to have an upper bound limit, which is going to be the worst case time, which is what we have right over here. So we have these two scenarios. They will occur 50% of the time each, which is why we have the 1 over 2 and the 1 over 2. Now the one on the left here, which is the good pivot, it's going to tell us that in the worst case, we are going to have 75% of our data to deal with, which is not that bad. It's still pretty, it's not the best, but it's not that bad. Now in this one that occurs 50% of the time as well, it's going to tell us that we'll have n-1 of our data left. That's a lot, right? That's a lot of data. This one's talking about at least a 25% kill on your data. This one's talking about a 1 kill. Not a 1%, a 1 kill, just 1 unit, which is bad. Now, the thing is that we don't have this in the master's theorem structure, right? The master's theorem structure wants a t of n to have an a, and then you multiply that by t, the recurrence t of your data divided by some factor that you're dividing it by, plus big O of n to the power of d. We've seen this in the master's theorem video, and that should start to be a bit more, familiar with you. So in order to get there, we need to bring that one of them to the other side. We know that they're in the same data type, and we just need to go ahead and rearrange it. And then we're in the master's theorem, and then we have our expectation time. We are expecting linear time, a big O of n. This is confusing. And if you have any questions, you leave them below and I will answer you. Believe me, I will answer you. It's a little bit confusing, but you guys should be able to get it just by reading over it and checking master's theorem videos again. Thanks for watching, and this will be the end of this video, and we will talk about some other things, some deterministic solutions in the next video.